Hello everyone. Today Capstone Project 2 Credit Card Default Prediction presented by Snehendu Jana. Table of content. In this content we have number of points. Number 1 problem statement, number 2 introduction, number 3 data cleaning, number 4 exploratory data analysis, number 5 handling class imbalance, number 6 transforming data, number 7 splitting data, number 8 fitting different model, number 9 cross validation and hyperparameter tuning, number 10 comparison of model, number 11 combined ROC curve, number 12 features importance, and number 13 is conclusion. Now, number 1 problem statement. In this problem statement, this project is aimed at predicting the case of customer default payments in Taiwan. From the perspective of risk management, the result of predictive accuracy of the estimated probability of default will be more valuable than the binary result of classification. So, we will predict whether a customer will default on his or her credit card. Now, introduction. Credit card are usually small plastic cards with a unique number attached to an account. It imposes the condition that cardholders pay back the borrowed monies plus any applicable interest, as well as any different agreed upon charges, either in full by the billing date or over time. Now, introduction. We have the data set of credit card clients contains 30,000 rows and 25 features, and the features are ID, unique ID of each client, limitation of balance, amount of the given credit, gender of customer, number 1 is male and number 2 is female. Now, education qualification of customer, number 1 is a graduate school, number 2 university, number 3 high school, and number 4 others. Now, marital status of customer is number 1 is married, number 2 is single, and number 3 is others. Then introduction. Age of the customer in years. Now, history of payment, repayment status in September, August, July, June, May and April 2005. Amount of bill statement in September, August, July, June, May and April 2005. Now, amount of previous payment in September, August, July, June, May and April in 2005. Here we can see the data cleaning. Data set contains no null values, no duplicates found, rename the features and replace some columns with categorical values. Here we can see the exploratory data analysis. Both the classes are not in proportion, which means that the data set is imbalanced. Data balance is required. Now, EDA. Female credit card holders are larger than the male credit card holders. As the number of female credit card holders is larger than the male, their credit card defaults are also higher than male. Here we can see that university and graduate school has maximum credit card holder. As the number of university and the graduate school credit card holder is higher, their credit card default are also higher. Then here we can see that number of credit card holders is maximum in single, but credit card defaults are almost same in the case of single and married people. Now, handling class imbalance. To balance the proportion, we have used a technique called SMOTE. What is SMOTE? Also called synthetic minority oversampling technique. It is the technique to make data class balanced. SMOTE works by selecting examples that are close in the feature space, drawing a line between the examples in the feature space and drawing a new sample at a point along that line. After that, we can see here handling class imbalance. This is the plotting of the dataset before and after the application of SMOTE. Now, the transformation of data. To scale data into a uniform format that would allow us to utilize the data in a better way for performing, fitting and applying different algorithms to it. The basic goal was to enforce a level of consistency or uniformity to dataset. In this picture, we can see that extract, transformation and next is load. Next is splitting data. Splitted the data into training dataset and testing dataset. Training dataset is for making algorithm, learn and train model. Test dataset is for testing the performance of their trained model. Here 80% of data taken as training dataset and remaining 20% of dataset used for testing dataset. Next is fitting different model. Following classifier used for prediction credit card default. Number 1, logistic regression. The next is decision tree classifier. Third is random forest classifier. Fourth is support vector machine. Next is gradient boosting and last is XG boosting. Now, cross validation and hyperparameter tuning. It is a resampling procedure used to evaluate machine learning models on a limited data sample. Basically, cross validation is a technique mainly used in settings where the goal is prediction and one wants to estimate how accurately a predictive model will perform in practice. Tuning the hyperparameters of respective algorithms is necessary for getting better accuracy and to avoid overfitting. Here we can see that logistic regression. Logistic regression is a machine learning algorithm for classification problem. In this algorithm, the probabilities describing the possible outcomes of a single trial are modeled using a logistic function. It is most useful for understanding the influence of several independent variables on a single outcome variable. Now, logistic regression. Base model. Train is 0.828, test is 0.832. Tune model accuracy is train is 0.827 and test is 0.832. Now, precision 0.795 and recall is 0.857 and 0.799 and recall is 0.855. Now F1 baseline model is 0.825 and tune model is 0.826. In the AUC baseline model is 0.833 and tune model is 0.833. Here we can see that decision tree classifier. Given a data of attributes together with its classes, a decision tree produces a sequence of rules that can be used to classify the data. Decision tree is simple to understand and visualize, requires little data preparation, and can handle both numerical and categorical data. In this chart, decision tree classifier. Accuracy. Baseline model train is 1, test is 0.971, and tune model is accuracy train is 0.837 and test is 0.824. Precision. Baseline model is 0.810 and tune model is 0.779. Recall. Baseline model is 0.781 and turn model is 0.857. F1. Baseline model is 0.795 and tune model is 0.816. And AUC. Baseline model is 0.792 and tune model is 0.827. Here, random forest classifier. Random forest classifier is a meta estimator that fits a number of decision trees on various subsamples of datasets and uses average to improve the predictive accuracy of the model and controls over fitting. The subsample size is always the same as the original input sample size, but the samples are drawn with replacement. In this chart, random forest classifier. Baseline model accuracy is train 1, test is 0.863 and tune model is 0.844 and test is 0.833. Precision. Baseline model is 0.821 and tune model is 0.794. Recall. Baseline model is 0.897 and tune model is 0.860. F1. Baseline model is 0.857 and tune model is 0.826. AUC. Baseline model is 0.866 and tune model is 0.835. Here, support vector machine. Support vector machine is a representation of the training data as points in space separated into categories by a clear gap that is as wide as possible. New examples are then mapped into that same space and predicted to belong to a category based on which side of the gap they fall. Random forest classifier. Accuracy. Baseline model train is 0.848, test is 0.840. Tune model train is 0.846 and test is 0.841. Precision. Baseline model is 0.765 and tune model is 0.678. Recall. Baseline model is 0.900 and tune model is 0.900. F1. Baseline model is 0.827 and tune model is 0.829. AUC. Baseline model is 0.848 and tune model is 0.849. Now, gradient boosting. It is a technique of producing an additive predictive model by combining various weak predictors, typically decision trees. Due to this sequential connection, boosting algorithms are usually slow to the learn but also highly accurate. The final models aggregates the result of each step and thus a strong learner is achieved. Gradient boosting. Accuracy. Baseline model train is 0.847, test is 0.843. Tune model train is 0.951 and test is 0.866. Precision. Baseline model is 0.801, tune model is 0.824. Recall. Baseline model is 0.875, tune model is 0.899. F1. Baseline model is 0.836, tune model is 0.860. AUC. baseline model is 0.846 and tuned model is 0.868. Now we can see XG boosting. XGBoost is a decision tree based ensemble machine learning algorithm that uses a gradient boosting framework. It is a perfect combination of software and hardware optimization techniques to yield superior result using less computing resources in the shortest amount of time. Gradient boosting. Accuracy. Baseline model train is 0.847, test is 0.843. Tune model train is 0.995 and test is 0.871. Precision. Baseline model is 0.799 and tune model is 0.831. Recall. Baseline model is 0.877 and tune model is 0.904. In F1, baseline model is 0.836 and tune model is 0.866. And in the AUC, baseline model is 0.846 and tune model is 0.874. Now the comparison of model. In classifier, optimal X boosting, random forest, optimal gradient boosting, SVM, optimal SVM, gradient boosting, XG boosting, optimal random forest, logistic regression, optimal logistic regression, optimal decision tree and decision tree. In optimal XG boosting, train accuracy is 0.995, test accuracy is 0.871, precision is 0.831, recall is 0.904, F1 score is 0.866, AUC is 0.874. Random forest, train accuracy is 0.999, test accuracy is 0.867, precision is 0.832, recall is 0.895, F1 score is 0.862, AUC is 0.869. Optimal gradient boosting, accuracy is 0.951, test accuracy is 0.866, precision is 0.824, recall is 0.899, F1 score is 0.860, AUC is 0.868. In SVM, train accuracy is 0.846, test accuracy is 0.841, precision is 0.768, recall is 0.900, F1 score is 0.892829 and AUC is 0.849. In optimal SVM, train accuracy is 0.846, test accuracy is 0.841, precision is 0.768, recall is 0.900, F1 score is 0.829, AUC is 0.849. Now, XGBoost shows highest test accuracy scores of 87% and AUC score is 0.874. Here we can see a chart rate and combined ROC curve. An ROC curve is a graph showing the performance of a classification model at all classification thresholds. An ROC curve plots TPR versus FPR at different classification thresholds. Lowering the classification threshold classifies more items as positive, thus increasing both false positives and true positives. Now, feature importance. Feature selection is the process of reducing the number of input variables when developing a predictive model. It is desirable to reduce the number of input variables to both reduce the computational cost of modeling and in some cases to improve the performance of the model. The next is conclusion. From the baseline model, a random forest classifier shows highest test accuracy and F1 score and AUC. Baseline model of random forest and decision trees shows huge difference in train and test accuracy which shows overfitting. After cross validation and hyperparameter tuning, XG Boost shows highest test accuracy score of 80% and AUC is 0.874. Cross validation and hyperparameter tuning certainly reduces chances of overfitting and also increases performance of model. Thank you very much.